Hi, everybody, and welcome to section 4.2 on vector spaces. This is going to be a super short lecture, and we're just really lightly touching on this topic. And partially because of that, and partially because this quote, the quotes I don't normally read on my lecture notes, but I'm going to read this one here today because it really speaks to perhaps what we're trying to do with this lecture in particular. And so this is a quote from a Cambridge mathematician. Mathematics is at least in part, the science of abstraction. Mathematicians look at the rich complexity of the real world and replace it with a simple system, which at best palely reflects one or two aspects of it. Roads become lines, towns become points, weather becomes a series of numbers of temperature, wind speed, and pressure, and human beings become units. The object is to show how useful such abstraction can be. And that really is the total gist of this lecture here. We are going to define what is a vector space. And so far, we've talked about two types of vector spaces. We basically have the one that we're super familiar with, the collection of what we've been calling vectors, which they're always vector things in vector spaces are always called vectors. But our vectors so far have been sets of numbers, lists of numbers. So we've had a vector in R2, 2, 3, a vector in R3, 1, 2, 3. And then we've been thinking of them as a directed line segment from the origin to the point indicated by the numbers in the vector. And we've also seen another vector space. We saw the collection of all matrices with real entries. So we're thinking of the collection of all matrices with real entries and thinking of each one of those objects, each matrix as a vector. Each one of those matrices is a vector in the matrix vector space. Okay, so those are the two examples we've seen, but there are many, many other examples. And so what we're doing is saying, rather than think of a particular example like Rn or R2 or R3 or any one of those R4, Rn as a vector space, it is a vector space, but rather than thinking of it as the only type of vector space, what we're thinking of is a vector space is actually a collection of objects. They can be kind of anything. We're thinking of just taking a collection of objects, and then we're going to allow two operations, addition and scalar multiplication. And that's what we've been seeing. Those are basically the two operations that allow us to form linear combinations. And then if this long set of rules here applies, then that collection is a vector space. If any one of these rules is breached, then that collection of objects, along with those two operators of addition and scalar multiplication, so if all of the rules hold, that it's a vector space. If any one of the rules is breached with those two operations, then it's not a vector space. So I mean, these are fairly basic things. This is right, closed under addition. Addition is commutative. Addition is associative. There's a zero vector. And that if we add the zero vector to any vector, we get the vector that we started with. Okay. There's a additive identity vector. So if we have the vector, some vector, we can take the negative of it. If we multiply by a scalar, we remain in the vector space. Multiplication by scalars is associative. The vectors distribute over scalar addition. Scalar multiplication is distributive, and there is some sort of a unit multiplicative identity element. So for the Rn vector space, for any Rn vector space, we have the identity element, the multiplicative identity element is 1, the vector 1 at the correct size, okay? And then we have, for example, in the only other vector space we've seen, the collection of all matrices over the real numbers, like that, we write that like that, the collection of all matrices of size m by n over, we say this, over the real numbers. That means that the coefficients in the matrices are real numbers. And we also have an identity element there, a multiplicative identity element, and we call that I. And we have it sized correctly for whatever it is that we're doing. So example, if we're working with 2 by 2 matrices, then that is the multiplicative identity element. It doesn't look at all like the number 1. You see the multiplicative identity element looks different depending on which vector space you're in. Okay, so let's just see how we would, for example, do something like demonstrate R2 as a vector space. What we would do is we would check every single one of these rules for R2 with addition and scalar multiplication. So we're considering the collection of all of the vectors in R2, and we're making sure that these are satisfied. I'm not going to go through every single one of them. What I'm going to do is go through a few of them, and then I suggest you stop the video and just check the rest of them. They're fairly straight. So what we're saying, for example, this first one is here. It says, if I take a vector x in R2, so x is going to be in R2, and y is going to be in R2. Okay, so let me just give an example. So x in R2 will look like this, x1, x2, and x1 and x2 are real numbers. Let me emphasize that one, x are real numbers. And that is what the meaning of this is here, a vector space over R. That is telling you from where are the scalar multiples being taken. The scalar, all these scalars in here, right? This S, these S and T's, those are identified as real numbers because this is a vector space over R. So some of you may have taken some more advanced courses. The vector space will be defined over a field. It doesn't have to be R, but in this case, it is R. So there are other fields other than R, and our vector space can be defined over that. Perhaps now just thinking back to the to the quote in the beginning, suddenly it's sort of a huge amount more abstract. You know, we sort of can get this idea of a collection of vectors that we can see, that we can draw, but then to suddenly say, well, actually we can think of these objects as whatever they are, so long as they satisfy these rules. And the big upside of this is that if we prove a theorem, or we observe something that applies to the general format of the vector space, then that immediately applies to all examples of vector spaces. So you don't have to reprove something for each particular vector space that you might be working in. You do it once and for all, and then you have it for them for all. So what you do is you sort of abstract the idea up a little bit, and then you are able to say things about a whole pile of objects all at once. Okay, so here we are. We've got one vector in R2, and we got a second vector here in R2. So I'm going to try to show that this first condition holds. So what I do is I simply go ahead and do this, x plus y, and that looks like this. And then x looks like this. So sort of by the definition of vector addition. And then I take a look at what this is here. And because x1 and y1 are real numbers, that is also a real number. And so is this. So that immediately tells me then, well, we have something that is exactly a vector in R2. So this is in R2. So I took two vectors in R2, I added them together, I got another vector in R2. That's what that first property tells. That has to happen. Okay, so now you just motor through each one of these things, showing that the property holds for the general object. You don't use a specific example, you use the general object, a general vector from the vector space. Okay, let's just do one more. Let's try to show this property here. Okay, so I already done x plus y. So let me write that down below. I've already done that, so I'll write it here. And then what I do is on this side, on the right hand side here, I'm thinking of adding this guy here, y plus x, like that, and I get a sum that looks like this. Okay, and then I'm trying to show that these two things here are equal. This guy here and this guy here. So now what I do is I think, okay, these are both real numbers. And so what I'm going to do is reverse this order here. And I'm allowed to do that because in some previous world, I have proved that the addition of numbers, real numbers, is commutative. Okay, so that I then rely on that to continue, and then I'm done. Okay, so you go through each one of these properties, showing that if every single one of the properties holds, you have a vector space. Okay, and just a point on the lecture notes, why do we do this? And so that's because if we we prove a result that applies to a general vector space, then that automatically applies to all vector spaces that we can dream up. Okay, so let's take a little look back at the subspace. We previously have considered subspaces of Rn. So let's now just sort of review that and generalize that to subspaces of a vector space. So here's the key definition right here. What is a subspace? A subspace is a non-empty subset. You're going to be careful to always check that you've got a non-empty subset. And then if it is that non-empty subset of V is closed, this is saying closed under linear combination. Closed under linear combination. Okay, so that might be done one of two ways. You could check if it's closed under addition and then closed under scalar multiplication, or you can do the two of them together, closed under linear combination. This is new. We haven't seen this before, and that's saying if S is a subset of a vector space and S is also a vector space, then it's a subspace. Okay, we haven't tried this one out yet because we didn't have the definition yet of a general vector space. So this would be another way of showing that something is a subspace. For where we're at, what we're doing really is just introducing this idea. We're treading super lightly on this. I'm not going to ask exam questions that force you to have like some in-depth understanding this. What I want you to do here is just, you need to be aware that there's sort of the next level of abstraction up. Okay, so what we would do here if we wanted to show something was a subspace, what we would do is confirm that it's a subset. And then rather than checking for closed under linear combination, which is what we've been doing prior, we would go and check whether all of those rules are satisfied for the set S. And then we would know it's a subspace. Okay, so let's just do two examples, and that's pretty much going to conclude on what we're doing. Okay, so this is a very short thing, and this is the limit of what I expect you to be able to do after this lecture. We're really not emphasizing this. Okay, so we're going to try to consider all the vectors in R4 with this property here: x1 plus 2x2 is 0, and we're asking, is this set a subspace of R4? So what we're doing is we're taking all the vectors in R4, and then we're picking out a portion of them. We're asking, okay, we picked out a portion of them. Clearly, it's a subset. Now, does that subset form a subspace? Okay, so let's take a look at that. I'm going to call this set that we're collecting out S sub A because it's example A. And so that is the set of vectors x1, x2, x3, x4 in R4. That's what that in R4, such that x1 plus 2x2 is equal to 0. Okay, so another way I could write that is this way here. That is, let's see, x1. I'm taking a look at this constraint here that we have on the first two variables. That is equivalent to saying that x1 is minus 2x2. So I can come over here and put x1 as minus 2x2, x2, x3, and x4. Okay, there. So the general vector in this set S sub A looks like this. And these guys x2, x3, and x4 are real numbers. That's how I write that. Okay, so clearly it's a subset, right? That we have, these are all, anything I generate via this method is a 4-component vector, and R4 contains all the 4-component vectors, so this is clearly a subset. Okay, so now we can, let's just identify, for example, 0 is in SA. Okay. As we've seen before, all subspaces have to contain the zero vector. Okay, the subspaces of R2 are the origin, lines through the origin, and all of R2. The subspaces in R3 is origin, lines through the origin, planes through the origin, and all of R3. Okay, the zero vector must be there. Okay, so we check that. We've got the zero vector in there. Okay, so now all we have to do is check that SA is closed under linear combination. Okay, so what we do to do that is we select two vectors in the set. So here's one vector. And here's the second vector. Okay, now let's form the linear combination. Looks like that. That is going to be minus 2sx2, sx2, sx3, and sx4, plus minus 2tx2, oh, sorry, let's not get that right. We're in the second vector. That is y2, ty2, ty3, and ty4. Okay, I'm going to add them together. And I get minus 2sx2 minus 2ty2, etc. I can go through all these ones, adding. Okay, now I think it's fairly obvious that all of these things here are, I mean, we've got a scalar times, this is two scalars multiplied together, two scalars, these are for sure all in R. Okay, and then let's take a look at this top component here, and let's notice that that is equal to minus 2 times sx2 plus ty2. Okay, and that is exactly the form that we need. All vectors in this set have the form minus 2 times x2, x2, notice those two things are the same, and then we've got x3 and x4. So it's closed under linear combination. By adding two vectors in this subset, we managed to generate another vector which is in the subset. So this is a subspace. So this set is, so we want to write that right there. We're happy to find out, yes, this is a subspace. Okay, let's try B. SB, the second set there, the second, we're going to look at all matrices. Let's think about this. What is M2 by 2 R? This is equal to all matrices that are 2 by 2, 2 rows, 2 columns with real entries. So we imagine this collection of all matrices, all 2 by 2 matrices with real entries. And we can clearly generate a couple of examples. So, I mean, this 1.26 pi there. That is a vector. We would call that actually a vector in M 2 by 2 with over R. Okay, now the question is, let's consider a smaller collection of objects, all of the matrices that are 2 by 2 that have entries that are integers. Okay, clearly it's a subset because we can have any real numbers in here. So if I just restrict that to the integers, we've got a subset. So this is a subset. SB is a subset. So we check that first, a subset of 2 by 2 over R. Okay, now the question is this a subspace? And the answer to that question is no, not a subspace. Might be a good time to stop the video and say to yourself, okay, I've been told the answer. How would I show that this is not a subspace? One of the something has to be violated. One of the zero vector. Was the zero vector there? Yes, the zero vector is there. Okay, so we have the zero vector. Zero is, I mean, that would look like this, zero, and that's clearly a 2 by 2 matrix with integer entry. So we have a zero vector. So that's not a problem. Now, so that means that leaves us with not closed under linear combination, and linear combination is scalar multiplication and addition. So why don't I just consider scalar multiplication, because that's easy. Let's take a look at scalar multiplication. Scalar multiplication, I'm going to pick any value of s that I want. Remember now I'm sort of going to show that it's not a subspace. I'm picking a real number because the scalars are chosen from the original field that forms the entries to the matrix. Okay, so there's a scalar there, and I take that and let me just multiply it by one of the elements that is in this guy right here. This matrix here is in the subset under consideration. I perform the multiplication. There it is. And voila, I have a matrix that this one is not in SB. So by using scalar multiplication, I escaped out of the subset that I chose. This is not a subspace. It's not closed under scalar multiplication. We're done. It's not a subspace. Okay, so that's the basic idea. This lecture is more of a review of what the difference is between a subspace and a subset. And then let's just do our final example. We've done that. We've done this one before. We're going to revisit this question. Commit to the answer before you listen to me say the answer. Commit yourself. Is R2 a subspace of R3? Okay. Now that you've committed, yes or no? Okay. What's the answer? The answer is no. It's not a subspace. Why not? Because R2 is not a subset. It's not a subset because if you consider the world of R3 and you collect up all the vectors with 3 components, how do you possibly get vectors with 2 components? They're not there. They're not even part of R3. Okay, so you can't even select the 2 component vectors from the big bag that contains all the 3 component vectors. So it's important that when you're checking if something is a subspace, you first confirm it's a subset, because of course, if you forgot this little thing here, you would then go and check this closed under linear combination, which it is. And then you may conclude erroneously that it's a subspace, but no, it's not a subset. Okay, so mostly this lecture has been a review of what is a subspace, and just to point you to the fact that we have seen actually 2 different types of vector spaces, and that is the tip of the iceberg. We're not going to go beyond that in this course at all. Okay, if you want an exercise to do, might be a good idea just to take this vector space and go through each one of the properties that a collection must satisfy in order to be a vector space, and verify each one of those. That's kind of a good exercise to see if you got the general idea of what's going on. Okay, and that is all. I'll be back. See you next time. Bye.